how the field is moving, and the molecule design or the drug design, we believe, is gradually moving from to a field where we can design and engineering the drug from the traditional process, and that's what I'm going to discuss with you. So first, let us try to see that what are the advantages that AI bring, and the last speaker spoke a little bit about that. Let's say when a new disease-causing target has been identified, disease-causing protein has been identified, we don't know anything about that which can be the probable drug which can cause the disease-causing function. So what people do, people try to take a library of molecule and try to screen that library and try to find some molecule which can probably go to the next stage. But this is a wasteful process because we know, as the last speaker mentioned, that there is a huge chemical space available which people has never explored. So what the AI method can do when it is trained with those existing molecules, it can first try to learn that grammar of those molecules so that it has ability to design many, many novel molecules. So we are not constrained with that small chemical space anymore. The other part is that there are many properties that one need to optimize. So once the molecules are identified, the primary thing people see that whether they have a good IC50 score or good binding affinity score. But then there are many other properties, like various ADMET properties, various toxicities, and people try to optimize them gradually one by one. So maybe after 3, 4, or 5 years, or maybe during the clinical trial, we can see that some of these properties cannot be optimized. So what we can do where AI can help is that while we are moving from this screening approach to the sampling this huge chemical space, we are not sampling randomly. We are sampling at a chemical space which is very specific to the target, that is measured through the binding affinity. And at the same time, we look at the various drug-like properties. So we can optimize not only one property, multiple property while we are sampling. So there is a reduced chance of late-stage attrition. So these are some of the AI models, the generative AI model. In the top, you will see that we have developed at least 4 generative AI model now, which we call as a ligand-based, which is kind of do based on the existing molecules. It try to optimize it further. What is really great is the structure-based method, and we have done number of client project based on this method, which is a de novo. We basically try to, okay, I'll come about that later. The third method, which we call as a gene expression or omics-based method, which is a truly personalized, but I think we have not reached there because there are not enough data, where we try to learn from various disease signature, and based on a new gene expression or omics signature, we can try to design molecules. And the fourth one, which we call as a forward synthesis-based method, because synthesize some of these AI-generated molecules can be developed. And during some of these meetings with various companies, we realized that. So now we also came up with a method where we, starting from a fragment, we try to grow these molecules so that we can get better molecules. At the same time, we work with number of predictive AI model, like things like various toxicities, the binding affinity, the IC50. What is crucial here is this multi-property optimization, because it allows us to optimize various properties in conjunction with the generative model so that we can get better molecules. So explainability is another important part, because now we have developed a method which we call as a which we call as a p-bricks, where we can give a fragment-based explainability, so that later on the medicinal chemist can find out that where is the problem of a particular molecule, let's say in terms of solubility, so that they can change that particular fragment. So now coming up again, so how it is possible, as we know that there is a huge chemical space, 10 to the power 60 or more. And now a molecule can be represented in various ways. As you can see in the right hand side, one representation is what we know as a SMILES, which is just given above that nitrobenzene. over there. So SMILES has a very dedicated way of representing a molecules. So when we represent that molecule in terms of SMILES format, now it's easy for us, easy for the machine to understand that language. And once it understands that language, it first try to learn that grammar, and then it has ability to design many novel molecules. We can do, we can also have predictive AI model, things like toxicity that I just mentioned in the previous slide. And then what happened that these generative AI model can design new molecules that you shown in the SMILES format, or one of the particular representation that the machine understand. And that is passed to the predictive AI model, things like binding affinity and toxicity. And if it is satisfied, then a reward is given to the whole model. So what is happening here is that otherwise it will be penalized. So what is happening here is that through this generative AI model in combination of the predictive AI model is gradually moving to a chemical space where all these properties are satisfied. I'll not go into the commercial projects that we have done, but just from one of our published work, I'll try to give you the advantage here. So here we are working with a particular target from a central nervous system, and as many of you know, that what is challenge here is that the molecule need to close across a barrier which is known as a blood-brain barrier. At the same time, some of the molecules, the molecular weight needs to be smaller in size, and the log P also controls some way how it crosses the blood-brain barrier. And the bioactivity is always important. Now, what I showed in the previous slide, through this same model, we try to apply all these as a reward so that the model can gradually produce target specific, which is taken care by the bioactivity model, and try to produce molecules which satisfies all these properties. You can include n number of properties that, like the various ADMET properties or solubility or some other properties as well. So I'll not talk about this particular thing, but what I'd like to say that there are a lot of other areas also we are working, like how we can work on the RNA as a target, because the number of proteins, we only, out of the 20,000 protein, only 700 or 800 are druggable. So we can expand this chemical this target space by moving to the RNA as a target, and that is one of the area we started from the scratch, and we have developed a comprehensive strategy how we can target the RNA as a target. So for the next few minutes, what I would like to say that what is important in this whole field is the data. And towards that direction, during the last 3 years, we have released at least 3 data sets. So one which we call as a RSIM, which is because we are trying to work with the RNA as a target, and there were not enough RNA-specific small molecule literature. So we tried to first work on release that RSIM. And we hear a lot about the synthesis method, but what I can say that there is still a lack of data. So we showed a approach how we can use various large language model to extract some of this reaction. And the third, just last year, we have done released a data set because we are interested about the bio-based synthesis, how we can use the microorganism for the synthesis. But there were not much method for the KCAT. I mean, there is a lot of data on the KCAT or the KM, but there were not enough data for with the protein structure, the complex of substrate and the protein. So the third work that we not only curated, but we also generated some data through through various bioinformatics method on how we can predict the KCAT and the KM. The last thing that I would like to talk a little about is that the success of this whole generative, the drug discovery will be possible to a larger extent when we try to include much more late stage properties, things like how we can be successful in the clinical trial. And although we have not done anything on that regard, but we are slowly moving also how we can, because the clinical trial is one major process where there is a lot of, I mean, we don't know much. I mean, we heard some of the things. So what we have done in this new work is that how we can generate virtual patients. We have also created digital twin. I think many of you may be aware that digital twin of human, the method which are known as the QSP methods. Although these QSP methods are great, but let's say we are trying to find the dose optimization for immunotherapy, and the normal approach is the give a higher dose, which might be problematic for the whole immune response of, or for the patients for who don't have a higher it depends on the patient variability. So we created patients with various tumor load, and then tried to use QSP model or the digital human team to find the response. But what happens that one need to give dose at various time point, let's say every 3 weeks dose over a 7 years or 8 years or 10 years, and there might be many possibilities like 3 mg dose, 5 mg dose, 10 mg dose, so which is a huge search. So we use this digital twin to try to find out what should be a response for certain doses, and use that as a training purpose for the AI model, so that we can do the personalized prediction for this huge number of virtual patients that we have generated. And then we come up with a clinical trial arm so that the companies can move forward with those particular dose. And the aim is to reimagine this whole process from the target identification. We have done a lot of work towards on the network biology side. The heat and the lead optimization are some of the part that I described right now. And also the clinical trial, we wish, and I think the field is moving towards that direction, where everything is coupled, because even in the pharma, people do not talk, one department do not talk to each other. That's what the observation. And if we can do or create a system which can talk between themselves only with the validated method, and that's what we have done in this architecture. This is just for the preclinical stage, where we start from a multi-agent system, from the target validation to druggability prediction to molecule generation, lead optimization, up to the synthesis. And right now, the aim is to look at the whole stage. I'm not going to show you the demo. This is, I thought that maybe I'll have time for doing this, where we started from the target. If the target is not available, we can go to the AlphaFold or something to generate that. But at each step, the human is important, and we only use those tools which are validated. These are some of the publications, and I'd like to thank some of the people who have worked in this field. Thank you. And I think, yeah. Thank you.
Hello. Thank you so much for your talk. I think this was the last talk. Thanks so much for every speaker, and you will get ample of time to interact with them. Only last one comment. Excellent presentation. And I always fascinated about the prediction methodology. And very good point you touch upon the virtual patient, how we can really reduce the toxicity. And only one suggestion for all those who are working in this field of AI based. So we have a lot of existing very good molecules for in oncology, which has a lot of limitation for their toxicity, though we have no predictive medicines and available. But repurposing of this medicine and actually how we can reduce this dosage so that the patient gets the benefit is the area which can be looked at. And on the lighter note, with a lot of good AI work with TCS is doing, I hope the stock prices start moving up. Thank you.